Swayam Prabha. Digital India. Educated India.
Okay, so good morning, good afternoon. Welcome back to this course on analysis and design of rigid pavements. We are currently in module 3, which is the analysis of rigid pavements using the finite element method. Now, just as a recollection of where we are in the course, so in module 1, we looked at, it was just a brief introduction to rigid pavements, but there we also saw that there are basically 4 types of rigid pavements. Jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRCP, and pre-stressed concrete pavements, PCP. Now, among these, I have pointed out that JPCP is by far the most widely used type of rigid pavement. And so for most of this class, we are essentially focusing on JPCP. CRCP is also used, but the analysis of CRCP tends to be a derivative of the analysis of JPCP. So largely, as we are studying JPCP, we are also going along while studying CRCP. Now, JRCP is used very, very rarely, and PCP is used for very specialized applications. So we're not going to go into those two in this series of lectures. Now, module 2 was the analysis of rigid pavements using classical methods. In module 2, I had told you that classical methods in a way basically means old methods. But what it means is methods that do not require any fancy computer implementation. It's not that you can't do them on a computer, but it's that you have a nice closed form solution which you could solve by hand if you wanted to. You could use maybe a digital calculator. You could use a spreadsheet program. But there was no need to write any sophisticated code in order to analyze those specific cases. Over there, we looked at Westergaard's theory. We looked at several modifications to Westergaard's theory. And we talked about several limitations of Westergaard's theory. We also considered dowel bars. We saw Freiberg's theory for analyzing dowel bars, both a single dowel bar as well as a series of dowel bars. And there also we showed that although we are doing our analysis, there seems to be several limitations along the way. So in module 3, we had briefly started by looking at multi-layer pavement systems. So the classical theories don't actually analyze multi-layer systems. They analyze slab on grade. But we saw that using certain analytical techniques of equivalent plate concept, we can combine a series of layers into a single equivalent layer, and then we retrieve an equivalent slab on grade system, which we could solve using Westergaard's theory or any other theory with all the limitations that come with it. And then once we solve for the stresses of that equivalent plate, we can then go back and calculate the stresses of the original system. Now, we looked at all of that, but truly what we need to start looking at is the finite element method, which is the modern way by which we analyze rigid pavements. Now, one note I should add, the finite element method is a vast area. I am no way claiming that I'm going to teach you the finite element method in a couple of lectures. We have about 3 lectures devoted to FEM for JPCP. It's going to be a very broad overview of FEM for JPCP. Largely, I'm going to show you some amount of mathematical formulation. But keep in mind, largely with FEM, we do not solve problems by hand. It's okay if you do it for practice in a class, but you don't actually do it by hand in practice. Instead, we have a variety of computer programs that do it. And we'll have a lecture where I'll show you some of those programs. I will show you some examples of how to use a specific program, which is called iSlab, which can be used for analyzing JPCP pavements. However, before we use these programs, we should be careful and we should understand what's going on behind them. It's quite dangerous to use a lot of programs without understanding the theory, because the problem is the programs can give you a solution. And if you don't have a good understanding on the limitations and the assumptions in these methods, you might assume that an incorrect solution is actually correct because you managed to get some solution. So keep in mind, in the finite element method, the reason we are learning the background of the finite element method as it applies to JPCP is so that we can understand the limitations of the method, and then we can understand how to use it carefully so that we can get reasonably accurate solutions. It's a very important term I just used, reasonably accurate, and we'll expand on that in today's lecture. Finally, let me add, before we go into today's lecture proper, let me add that the finite element method is, as I said, not something you can learn in 2 or 3 lectures. I assume most of you are civil engineering students or have a background in civil engineering. I strongly recommend you take a course, whether it's an undergraduate course or postgraduate course, in the finite element method. It's an extremely useful method. Virtually every branch or every specialization of civil engineering and other fields of engineering have been touched by the finite element method. So it's a very useful method. It's very important to take a full-fledged course on it. But for this course on analysis and design of rigid pavements, in today's lecture, which is lecture 17, I'm just going to give you a brief view on the overview and the need for finite element method as it relates to jointed plain concrete pavements. Okay, so today's lecture, the objectives will be as follows. First of all, I will list various shortcomings of classical methods. It's somewhat of a review of what we learned, but some of it might also be new. And then I will explain the principle behind the finite element method and its advantages. In today's lecture, we will not actually see the full formulation for FEM for JPCP. We'll have 2 more lectures after this, where we will go into the details of that formulation. Today, I just want to give you an overall idea of what the principle is and see what are the benefits of the finite element method. Okay, so what I want you to recall is that we had derived a particular equation, which is the equation which I have over here. This was the Sophie-Germain equation, plus with a correction factor which was added for the subgrade, which was modeled as a Winkler foundation. So basically, this is the governing equation of a slab on grade or JPCP. And this is what we were looking at previously. Just as a reminder, so this D over here is the plate stiffness. So this was EH cube divided by 12 into 1 minus mu square. So it's a scalar constant. W was the plate deformation. So we assume that for the plate, there is no shear deformation. So whatever shear deformation we have on the top, the same amount of deformation we have on the bottom, and the same amount of deformation we have anywhere across the cross section. And so we actually just solved the plate along the neutral plane, which I've drawn over here. We are going to solve the plate only along the neutral plane, and we only solve for its deformation, the transverse deformation, which is W. And so that's why we have this particular equation over here. Now, we saw many analytical solutions starting from Westergaard's theory. So in Westergaard's theory, as a reminder, we had 3 solutions which Westergaard came up with. One was when the plate was loaded in the interior. So what that meant is the plate has certain joints, or the JPCP has certain joints. The joints were assumed to be very far away, and then we had the load somewhere in the interior. Or we looked at the case when it was loaded at the corner. That is, we had 2 edges, they intersected at a corner. We put a load, but we assumed the other 2 edges were very far away. Or we had case of loading at the edge, where we have one edge, we placed the load at the edge, and we assumed all the other loads were very far away. That was basically the essential idea of Westergaard's theory, as well as the idea of several corrections which have come around. Now, all those corrections made various assumptions around the solution technique, but all of them stuck to this basic assumption that the slab size is very large. So that was one assumption which all analytical methods made. Another assumption which analytical methods made was called tension springs. So we assumed that, as I mentioned previously, we assumed that the plate is sitting on a bed of springs. Now we assumed that if the plate has a deformation, the deformation can either be downwards or it can be upwards. In both cases, we said that there is going to be a reaction force, which is this KW term, which is coming from this bed of springs. Now, if the plate is pushing downwards, that means the springs are in compression, then the reaction force is KW, that's fine. But if the spring is pushing upwards, then the reaction force is minus KW, which is to say that physically what we are assuming is that the plate is not, when the plate is pushing against the ground, that the ground is pushing back. That seems reasonable. But we are also saying that when the plate is moving upwards due to load, due to climate or temperature effects, whatever, when the plate is moving upwards, then the ground is trying to pull it back downwards. That's what we mean by tension springs, that the springs on the ground allow some amount of tension and they will resist that tension. In practice, this is not what happens in real life. Of course, now you can try this yourself. Go and stand on the ground. When you're pushing against the ground is supplying a reaction. That's how you're able to stand in one place. But when you lift your leg up, the ground is not trying to pull your leg back down. So this assumption of tension springs is clearly in violation of what we see in reality. We actually need a situation where we insist that K is 0 when W is upwards. So we actually write it typically like this, K plus, that we only allow springs to be in compression, and when springs are in tension, we assume that K is equal to 0. That's what this K plus symbol means. We cannot analyze that technique using analytical methods. It actually becomes a nonlinear system of equations in that case. So we can't actually solve this technique using analytical methods. Another assumption that these techniques made was a rather simplistic footprint. So for example, Westergaard's theory straightaway assumed that all the tire footprints were circular. We saw some other theories which made some modifications to that, and we were allowed to have square footprints. But something as simple as a rectangular footprint, which by the way is also a very simplistic assumption. We'll see a more complicated or realistic scenario in today's lecture. But just that, the shape of the footprint, we had to simplify it to something which is pretty unrealistic just to be able to get these analytical solutions. We also considered that the plates had uniform properties. So we didn't have the option of, for example, in reality, if you had a particular JPCP where, let's say, some piece of the slab was broken off, and so then it was replaced by some other material, which is what we call patching. So if we patched it with some other material, the fact that we have two different regions of the JPCP, so some part of the JPCP has a particular property, some part has other material properties, we could not analyze this using classical methods. Whereas in reality, this is a fairly common case. JPCB patching does happen. You'll probably see it quite a lot if you go out on the road on any rigid pavement. So we can go on, but these basically tell you that these analytical methods have many, many limitations. There are many simplifications which are made, and there are limitations in terms of what sort of cases we can analyze. Many cases which are actually very close to physical reality, that is what we actually observe in the field, those are very difficult to impossible to analyze analytically, and certainly the analytical solutions which we have at present, Westergaard's method and their modifications, they are simply unable to handle these additional assumptions. So let's look at some results or some implications of these. This is somewhat of a summary of what we had talked about in one of the earlier lectures. So what I have here is, suppose we have an interior slab, that is, again, we have a slab where the joints are assumed initially to be very far away. That solution, when you have interior loading, is Westergaard's solution. Now, what has been plotted over here is slab size. Of course, it's been non-dimensionalized. So this is L over L. So this is the slab size divided by the radius of relative stiffness. So this is just a non-linear measure of the size of the slab. And on the y-axis is shown a solution. That solution can be deflection or it can be bending stress. We'll look at both. But what we are shown is a solution, again, for certain set of cases in terms of the dimensions of loading, etc. But we are shown the solution as a percentage of Westergaard solution. So Westergaard solution is basically when you have a very, very large slab. So first of all, we'll look at deflection. So what we see is, as expected, when the slab size is very large, then the solution, and this solution, by the way, was obtained using finite element methods. So I'm not telling you yet how we obtained them. Just understand that we've obtained them using finite element methods, whatever that particular method means. Okay, so what we see is when L over L is very large, in this case, actually, when L over L is somewhere around 9 to 10, then we actually end up with deflection, which is almost the same as Westergaard's deflection. So it's just about at this 100% mark. But at more reasonably sized slabs, so relatively smaller slabs, maybe around 3 to 4, so in this range over here, we see that there is some deviation. That the Westergaard solution, our numerical methods tend to have a higher estimate of the deflection as compared to Westergaard solution. Or in other words, Westergaard solutions tends to underestimate the deflection when you have smaller size slabs. Okay, let's look at bending stresses, because as I mentioned, when it comes to performance, we are basically concerned about bending stresses more than we are concerned about deflections. So when we look at bending stress, what we see here is, as the L over L increases, that is, as the slab size increases, there seems to be some amount of constant difference between Westergaard solution and the analytical solution. In particular, the difference is actually less than 100%. So what that means is, Westergaard solution seems to be overestimating the stresses when you have interior loading. Now, on the other hand, when we go to relatively smaller slabs, so we go down to this range of maybe 1.1 to 2 in the L over L ratio, and we see that that difference is just getting larger. So over here, for example, just roughly speaking, perhaps the analytical solution is 50% of Westergaard's solution. So Westergaard's solution is, roughly speaking, estimating a value of bending stress which is double of the value which we're getting for numerical solutions when we look at smaller slabs. So this is one example to show that of course, the deflection and the bending stresses do depend on the size of the slab. And size of the slab is something we have so far never seen in our calculations. If you go back to the lectures which we did on Westergaard's theory and the improvements in Westergaard's theory, you will see we never had slab size as an input, because Westergaard's theory just assumes that it's a very large slab. But from this diagram, you can clearly see that there are significant differences that arise when you make this sort of an assumption. It is a major simplification. It does not match at least what the finite element method gives us. Now, whether that finite element method is correct or not, that's something we'll talk about today. Here's another shortcoming. So, of course, one shortcoming we already talked about was tensionless springs. The fact that the spring, when this slab is pushing downwards, then the spring is providing some reaction, that's fine. But when the slab is actually pushing upwards or it's bending upwards, then the ground is trying to pull it back down. That's not what reality is. So we cannot analyze tensionless springs using classical methods. Another issue is realistic footprints. So here what I have is just a picture I got from Wikipedia. This is actually what the actual contact footprint of a typical tire for a truck looks like. So I'm sure all of you have seen a tire of a truck. They have those treads on it. They're mainly there to provide friction. So basically what they do over here is they drive these trucks on a pressure plate, and then they look at what sort of pressure distribution they're getting. That's what this image is. And a relatively easy way to do this without getting the numerics is that you could actually just drive a tire, let's say, over some ink and some paper, and you can see what the distribution or what the footprint of the tire is. So this diagram which I have over here, it gives an example for a certain tire. Every tire has its own footprint. Every manufacturer designs it slightly differently. So this is obviously just one example. But what we see over here is, first of all, it's not circular. That I think is quite obvious from the diagram. We see that it's not circular and it's a non-uniform distribution of pressure. So around the middle over here, which is basically where you have the seam of the tire, you tend to have a higher stress, and then further out towards the edges, the pressure or the stress becomes much lower. So you have a non-uniform distribution of pressure. The footprint is definitely not circular. Moreover, not only is it not circular, at the points where you have those treads on the tire, you actually do not have a footprint altogether. So the footprint itself is broken up into pieces which have no particular shape. They have somewhat of a semi-arbitrary shape. Compare this to the Westergaard solution or the solution from the improved solutions of Westergaard's theory, where we can have a circular load, or at best we can have a square load. I think you'll clearly agree with me that this is definitely not nearly close to what we see in reality. Another shortcoming, which I had already talked about, is patching. That if we have a JPCP section and for whatever reason, maybe we had some corner cracking, and say the municipality or whoever owns the road decide to go in and just patch this by putting some more concrete over here, just removing the old concrete and pouring a triangle of new concrete, a triangular wedge of new concrete, very good chance that this new concrete and this old concrete are going to have different properties. So the fact that the same slab might have a non-uniform distribution of material properties is what we call patching, and that is not possible to analyze using Westergaard's theory or any of the improved theories that we had. One basic assumption was of all these theories that the entire slab was uniform, linear elastic, and isotropic, and so we cannot actually analyze this particular case using Westergaard's theory or any of the other theories. Another example is loss of support. So we had talked, if you recall previously, about a type of distress which we called pumping. So pumping was, for example, here you had an approach slab and you had a leaf slab, and then you had a load on the approach slab, and that was causing the approach slab to bend. Many times what happens due to pumping is that what happens is this load goes from the approach slab to the leaf slab. So you have an alternating series of slab deflections. When the load is on the approach slab is bending. When the load goes on the leaf slab is bending. So you have this alternate series, and what pumping is that when water is come into the base layer or the subgrade layer, whatever is below the surface, it causes ejection. You get pore pressure developing, and that pore pressure causes ejection of fine materials through the joint up into the surface of the pavement. Now, this is going to manifest on the surface as basically a very muddy and dirty looking pavement. But what it's actually doing below the surface of the pavement is it's creating a void over here. Because you are physically losing material, you are getting an area where you have a void just below the joint. When you have a void just below the joint, you basically do not have anything to support the slab at that point. Just in that small area near the joint, we say that the slab has lost support. Now, that can have some very serious implications on stress. It is very important that we will analyze this situation. We critically analyze and identify these situations. Unfortunately, the classical methods can't do it at all. The classical methods, again, assume that the slab is continuously sitting on a bed of springs, and there is no option for us to say remove the springs in a small part, in which case we would be able to analyze the case when we have loss of support. So we do not have this sort of an option, or we do not have this sort of an ability with the classical methods altogether. So these are the various shortcomings of the classical methods. And it's really why, because of this, that we have started in pavement engineering and design of JPCB pavements and analysis. We've started in, let's say, in the last 30 years, I would say, we've really been moving into using the finite element method in a very big way. So all of these shortcomings which we just discussed, they are very hard, or in some cases even impossible to resolve through classical or analytical methods. If it could be resolved, it would end up creating an expression which would have it's a summation going to some infinite number of terms or something of that sort. So even if we could get a solution for these particular type of problems, they would be really, really complicated solutions. It's definitely not something that you could easily program into a spreadsheet, or certainly not something you would do by hand. So it could, even if the solutions exist, they can be so difficult to actually calculate that they are as good as the fact that we don't even have them. So these shortcomings are very impossible or hard to overcome using the classical methods. However, they may make a big difference to the critical stress. Just now, the example I gave was loss of support. So if I have this Winkler foundation for a part of the slab, but close to the joint I have a void, so effectively I don't have any support, it is going to make a very, very large difference. Remember, this little piece here is effectively a piece of plain concrete. There's no reinforcement. It's a piece of plain concrete which is now undergoing tension at one particular part without any reinforcement. It's very weak in tension. So you can have very high stresses developing very rapidly, and therefore you can have deterioration occurring very rapidly. If we are unable to analyze this, then clearly we have a shortcoming in our techniques for analysis. So therefore, we need an alternative method for solving the governing equations. That alternate method is going to be, which is used in practice, is the finite element method. So let's talk about what is the idea of the finite element method. Before we even go into how do we use it, the real question is, why do we use it? What's the basic philosophy? Now, I clearly said here, we have analytical methods which have certain shortcomings. So what are the benefits of the analytical methods? Of course, one benefit is it's easy to calculate. You can do it by hand, you can do it on a calculator, you can do it on a spreadsheet. So relatively simple to calculate, therefore nice to give on a homework assignment or something of that sort. But the main and actual advantage of analytical methods, which is why they are still preferred to this day in many parts of the world, is that these analytical methods give us exact solutions. If the assumptions are correct, then that is, if the slab is very large, if you have continuous support from this subgrade, etc. If all of these assumptions are correct, then we know for sure that our analytical solution is correct. The differences between analytical solutions is the assumptions they make about maybe the type of loading or whether you include shear or not, but it's not the correctness of the solution. As long as you agree with the assumptions of the method, the solution carries no error at all. So, but the first thing we have to understand is, in engineering, we really don't care about solutions having 100% accuracy. The real reason for that is, in engineering, nothing is 100% accurate. When you actually go out and do construction, and maybe some of you have had a chance to do an internship or gone to a construction site, when you actually go out and look at a construction site, you'll see there's so much variability on the ground. The concrete, some amount of concrete is setting, some amount of concrete is coming in a truck, it has freshly been mixed. There is some differences in workmanship. Sometimes there's a little patch of the ground is wet, a little patch of the ground is dry. There's a whole variety of things that can happen. And so in engineering, we do not even expect to have 100% accuracy. So With that assumption, if in the field, in practice, we don't have 100% accuracy, what that means is our analysis techniques don't really have to be 100% accurate. Now, I'm not saying we are okay with a completely wrong solution. No, we want a reasonably accurate solution, but we do not actually need a perfectly accurate solution. So the first thing to understand in the finite element method is we give up on the idea that we are going to get a perfectly accurate analytical solution. We accept that there will be some error in our solution as compared to the true solution. Now, I should add the true solution for many of the cases may not even be known. Certainly, we could, this particular plot which I showed over here, where you had the solution from a numerical method, which is the finite element method, as a percent of the Westergaard method, we assume the Westergaard method for this particular interior loading case was a true solution, and that's a good assumption. But in many cases, for example, many of these shortcomings which I showed in the slide, in many of these cases, we don't even have a true solution. So first of all, we make an assumption that whatever solution we get out of our finite element or numerical method, it's not going to be accurate. It's going to have some amount of error on it as compared to the true solution, if we even knew the true solution. But the truth is, in most cases, we don't even know what the true solution is. But we at least have an estimate of what the error is. How much error are we willing to tolerate? Generally, in the finite element method, now it depends on the application, but for linear elastic finite elements, which is what we will study in this particular class, around 1 to 5% or even less is a sufficiently small error. You will agree with me that 1 to 5% error is genuinely a very small error. That much error you can get during using analytical methods in just making a slight round off, that you don't carry it out to 16 decimal places, you round off the stress, say at 1 decimal place or 2 decimal places, you can make that much error just because of a round off. Similarly, in the field, I just mentioned there are many uncertainties that happen in the field. And so those uncertainties can lead to a variance of maybe 1 to 5%. For example, if you wanted to evaluate thickness, 1% deviation of thickness in different locations of this pavement, that's quite normal actually in construction. So the fact that we are carrying this 1% to 5% error in our analysis is actually okay for most practical applications. So first of all, in the finite element method, we straight away start with the assumption that we are going to have an error in our solution. We are not looking for an exact solution. We are looking for a solution which has some error, and we hope that error is relatively small. That's something we have to come up with a method that sort of guarantees that. But we accept the fact that we will always carry some amount of error in our solutions. Okay. So the solutions which we get out of the finite element method, because they have some error, we can say that they are approximate solutions. So remember, whenever you hear a statement, it's commonly made, you will hear statements such as, the problem was solved using the finite element method. That's fine to say, but really, strictly speaking, if it was said correctly, what the correct way to say that statement is, the problem was approximately solved using the finite element method. We do not get a completely accurate analytical solutions using FEM. We get approximate solutions. So these approximate solutions, now one of the main assumptions of the finite element method is, previously what we were doing in Westergaard solutions, we had a particular load and we could calculate the stress at this point. We move the load, we calculate the stress at any other point. So what we see is that we have a continuous system. Our slab is a continuous object. We can put the load at different points over there, and using the analytical methods, we can get a solution. The idea of the finite element method is we cannot get the solution at every point. So I cannot pick a random point and expect to get a solution in the finite element method. Instead, what we do is we derive these approximate solutions at a finite set of discrete points, which are called nodes. So first of all, we take our slab or our structure or system, whatever it is, we take our domain generally, and we are going to discretize it into a series of nodes. It's going to be a finite number of nodes. And those nodes are where we actually are going to solve a solution for. So whatever we're solving for slabs, for example, we're interested in the deflection or the stresses. Those are going to be calculated at the nodes only. The nodes in turn are connected by a finite set of elements. So we have a finite set of nodes, and those finite set of nodes are connected through a finite set of elements. That's also why, by the way, it's called the finite element method, because we have a finite set of elements in which we've discretized our system. So to summarize, the basic assumption we have in the finite element method is we do not have an exact solution. We have an approximate solution. Moreover, we don't have the solution everywhere in our domain. We have a solution at a discrete set of points, which are called nodes. And those nodes are connected by a discrete and a finite set of elements, and hence the name finite element method. And so the challenge of developing a finite element method is to actually figure out what are these elements and how can we express our differential equation in the form of these finite elements. So that's what we look at in the following slides. How do we then figure out how to discretize our differential equation in the form of these finite elements? The way is we do it as follows. So as I said again, if we have our slab thus, we are not going to solve the solution everywhere. Instead, we discretize it into a finite number of nodes, and then those nodes are connected by elements. Within each element, this is the key part of the finite element method. Within each element, we assume that the solution varies according to some sort of polynomial expression, or that it has some particular shape. So that could be linear, quadratic. Okay, just to convey the same idea in a slightly different way, suppose we have this curve. This is some sort of a solution. We do not have the solution exactly at this curve. So obviously this is some kind of a non-linear curve. Instead, we say that the solution, somehow we're going to calculate the solution only at a discrete set of nodes. In between those nodes, we are going to assume the solution is, there are many assumptions we can make, but we can assume the solution is linear. So I'm drawing the solution using these dotted lines. Obviously, you can see that the solution is not linear in reality. The actual solution which I have has some amount of curvature even in between nodes, but we're going to assume the solution is linear. So one of the biggest assumptions in the finite element method is that while we are calculating our solution at these discrete nodes, in between the nodes and within each element, so in between the nodes and within each element, the solution is assumed to have some arbitrary shape, which could be linear, it could be quadratic, it could be cubic. There are many options which can be used. So this shape is going to be defined by a function. It could be a linear function, it could be a quadratic function, etc. Generally, this function is called a shape function. So shape functions, and again, I encourage all of you to take a formal class in finite element methods. You'll learn these in much greater detail. But a shape function is basically that simple. It is what shape is the solution in between the nodes and within an element. And by shape, it could be linear, it could be quadratic. So what is the actual shape of the function? Now, what happens in the finite element method is we have a differential equation. So for example, we have the Sophie-Germain equation with the correction, which we've been using for pavements for JPCP so far. This equation, as we saw, is quite difficult to solve. But fortunately, Westergaard and others solved it, but they solved it for a lot of simplified assumptions. What we can do is, in the finite element method, we do not solve the equation. Actually, we don't solve the equation. We instead convert this differential equation into a large system of algebraic equations. So first of all, it's a system of algebraic equations. We are solving the solution at these discrete nodes, and therefore, as many nodes that we're solving for that many, it's a little more complicated than this, but as many nodes that we're solving for, we convert the differential equation into that many equations. So for example, if we discretized our slab into maybe 9 nodes, which are shown over here, and suppose we're interested in 9 solutions, so one solution at each node, then we're going to convert our differential equation into a system of 9 algebraic equations. And algebraic equations, we know how to solve, right? Well, the truth is, if I asked you to solve a system of 9 algebraic equations, you would have quite a hard time doing it. So although we can, and 9 is actually a very small number. More likely in the finite element method, you will have thousands, even hundreds of thousands and millions of equations that you have to solve. So obviously, you're not going to solve it by hand. Fortunately, computers are actually very, very good at this. Starting from the 1960s, many good algorithms, which are sometimes called basic linear algebra subroutines and linear algebra package. So there are many good algorithms which have been developed for digital computers to solve very large system of algebraic equations. So the main principle we use in the finite element method is that we are going to take our differential equation, which is otherwise very difficult to solve. We are going to somehow convert it into a series of algebraic equations, and it's going to be a very large number of algebraic equations. And then we give those equations to a computer, and we let the computer solve the system instead. That's the basic idea behind the finite element method. This also why, by the way, the finite element method, the idea of the finite element method is actually quite old. It's over 100 years old in terms of how to do this. But the reason the finite element method has really picked up in the last 20 to 30 years is because computers started becoming cheaper, computers started becoming faster and more powerful only in the last 20 to 30 years or so. So the finite element method is still, on the grand scale of engineering or civil engineering, it's still a relatively new method, but it has truly revolutionized the way we work because computers have made it so much easier to solve this very large system of linear equations. Okay, so that was all a little bit vague. What I wanted to do is I wanted to take you through an example. So the finite element method, as I said, can be used to solve any differential equation. That could be an ordinary differential equation, it could be a partial differential equation. It doesn't matter. But the finite element method can be used to solve any differential equation. Now, of course, we are interested in solving the Sophie-Germain equation, which is what governs our JPCP behavior. But before that, what I thought is, let's go through a relatively simple example. And I'm sure all of you have seen an example like this in either your high school or maybe your BTech first year mathematics courses. You've seen some equation like this. So I wanted to show you how this particular pretty arbitrary equation, it doesn't really have any physical significance. I wanted to show how the finite element method can be used to solve this particular equation. And through that, I wanted to illustrate the benefits and the shortcomings of the finite element method. So what I have here is, suppose we have this ordinary differential equation, ODE, ordinary differential equation. Suppose we have this ODE, d square u over dx square. So it's u is the unknown variable that we're trying to solve. Therefore, u obviously is a function of x. D square u over dx square plus u is equal to 2x square. Now, this is the differential equation. Generally, we will not get a unique solution to this. Actually, not generally, always. We will not have a unique solution to this if we don't also provide certain boundary conditions. So what we do is we say that the boundary, so we say that this u of x is defined in x from -1 to 2 in this particular example. So the domain of the problem is -1 to 2. And we specify some boundary conditions. Now, you can have fairly complicated boundary conditions. I don't want to go into too much detail over here, but we can simply write in for here, we assume the boundary conditions are that at the boundaries, that is u of -1 and u of 2, the value is simply 0. So we said u of -1 is equal to u of 2 is equal to 0. That's the boundary condition we use. Again, you can have very sophisticated boundary conditions. It's not important in this class. Now, one thing to understand about this differential equation, unlike, say, real life when we are solving for a pavement, when we have many uncertainties and we therefore cannot actually calculate an analytical solution, in this case, because we have this nice little differential equation, we actually have an analytical solution. So the analytical solution, and full disclosure, I derived this using Mathematica. I didn't solve this by hand. The solution is over here. This, by the way, this CSC is this cosecant, which I'm sure all of you have seen in your classes in trigonometry. So what you will agree with me that this is a pretty ugly looking equation, this solution. It's certainly possible to calculate it. And of course, I wouldn't put it beyond, say, many professors of mathematics to actually prescribe this maybe in an exam or in an assignment. But for us who are civil engineers, it would be very difficult to actually calculate the solution. That's actually why I've taken this problem. So this is a problem where we have an analytical solution. It's just pretty difficult to calculate. There are many cases where we may not even be able to calculate an analytical solution. It might be too difficult, or it might, even if we can do it, we can't actually evaluate it because it might have some infinite sum or something of that sort. So, but anyway, I want to take this particular problem because it has an analytical solution, but it's a fairly complicated looking analytical solution. It would be quite cruel as an engineer if I asked you to actually solve this. We are going to try to solve this using the finite element method, and we will also compare it against this analytical solution. Now, just to illustrate, it's usually nice to actually see this in terms of figures. So this is what the analytical solution looks like. So it's not quite a parabola, but it has some sort of a parabola-like shape. So I'm not going to say it's a parabola. It's not. It's this complicated trigonometric function. But it has some sort of a parabolic or a sinusoidal shape, if you may. So obviously, it goes from -1 to 2. That's the domain. We don't have a solution beyond the domain. We should not actually be trying to plot this beyond its domain. It's not valid beyond its domain. And here you can see that it seems to have some kind of low. So it goes from 0 on either side of the boundaries, and it takes on some negative values. And the minimum value or the most negative value, whatever you want to say, but this minima, it'll come to around, I believe this is like 18, -18 or -17.5, something of such. We'll see the more detailed solution later. So that's something we know, that the solution has this parabolic-like shape or the sinusoidal shape, and its minimum value analytically is -18, -17.5. That's an important value to know. We will keep coming back to it as we go. Okay, so as we said previously, the first step in the finite element method is we do not solve this solution at every point. If you take a look at this analytical solution, you'll see that for every point along this solution, so I can put in any value of x. I can put x is equal to 0.5. I can put x is equal to 0.55, 555, so on. As many decimal places as I want, I can keep plugging in x. I just put it in this equation over here for the solution and I'll get the solution. So I have a solution at every point. That is basically what an analytical solution is. Another way to write this as an analytical solution has infinite precision. Infinite precision. Regardless of how many decimal points we have, we can calculate the solution at any point that we want. Of course, there are limitations to computers because computers have finite precision. They have 64-bit computers generally have 16 decimal places that they can hold. But that issue aside, we basically have an analytical solution which has infinite precision. Straight away, our first assumption in the finite element method is we give up the idea that we can solve this at every point. In other words, we bring the solution down to finite precision. Right? So we are not going to solve the solution at every point. We are only going to get the solution at a discrete set of points, which we call nodes. Of course, these nodes are going to be connected by certain elements. So the first step in any finite element solution is we take our domain. Again, the domain here was this -1 to 2. We take our domain and now we choose a discrete set of points at which we want to solve this system of equations. Let's start with the easiest example. Suppose we have only one element consisting of two nodes. So again, we have our domain. It goes from -1 to 2. We can discretize this into a finite set of points. Let's say we choose to do it to a finite set of just 2 points or nodes, which is x is equal to -1, and let's call this x1, and then x2 is x is equal to 2. And then of course we connect these using one element because two nodes can be connected at best with one element. So this is now our discrete system. We are no longer trying to solve u of x, where x can be any value from -1 to 2. We are not doing that. What we're actually trying to do is we are trying to solve u at x1, which I'm going to use this notation is equal to u1, and u of x2, which I'm going to use this notation u2. We are only trying to solve u1 and u2. In between u1 and u2, so at any other point in between the nodes, we are going to assume that there is some shape of the solution. Actually, we'll assume it's a linear shape. So we'll assume that if we know u1, for example, and if we know u2 somehow, then the solution in between is going to be a straight line. That's our assumption. Note here, if you look at this figure I have over here, the solution in between any 2 points is not a straight line. It's a sinusoidal or a parabolic-like curve. There is a curvature. It is not a straight line. But I'm going to make this assumption, and that's part of the finite element method. I'm going to make this assumption that the solution is actually a straight line in between our nodes. Okay, so what we need is we need to get an equation of this straight line. So what I have is I have at x is equal to x1, I have u is equal to u1, and at x is equal to x2, I have u is equal to u2. I need to write some equation, which is going to be a linear equation, that relates u of x at any point with x1 u1 and x2 u2. There are systematic ways to do this. There's something called Lagrange interpolants, etc. It's beyond the scope of this class. Again, I encourage you to take a formal class in the finite element method where you learn a lot of these in greater detail. But without going into too many details, this is what it's interpolating solution or the interpolating function looks like. U of x is equal to some function of x into u1. u1 again is a constant, unknown constant, but a constant. So it's some function into u1 plus some function into u2. Let's check if this solution is correct. So suppose to this u of x, we plug in x is equal to x1. When x is equal to x1, we must have u is equal to u1. Our interpolating function or our expression must give us that for it to be correct. Okay, if I plug in x is equal to x1, what you'll see is this second term over here, this coefficient of u2, the numerator is x1 minus x. So if I put in x is equal to x1 over here, this is going to be 0. So effectively, I'm going to do 0 into u2. And so 0 into u2 is just 0. So this term goes. Over here, for this first expression, which is the coefficient of u1, if I plugged in x is equal to x1, you will see I get x1 minus x2 in the numerator. the denominator also happens to be x1 minus x2, and therefore this expression evaluates to 1. And so I will get u of x is equal to x1 is equal to u1, which is exactly what I wanted. I will leave it to you as an exercise to prove that at x is equal to x2, you will get u is equal to u2. Please do that on your own. You will see that this form of the expression is correct, and you will indeed have this, that u of x is equal to x2 is equal to u2. So that tells us that this expression that we've developed, which is telling us the linear variation. Again, it's an assumption. It's telling us the linear variation of the solution in between the nodes. This expression is correct. Could we have come up with a more sophisticated version? Could we have done some kind of a quadratic assumption instead? Yes, we could. We won't go into that. Again, you need to take a formal class in the finite element method to know these things which are called higher order methods. But we're not going to go into that detail. Now, in the finite element method, we generally like to express everything in the form of vectors and matrices. It just gives us a very compact sort of notation. So I hope you learned this notation, that whenever I have a vector, for example, if u is a vector, I show it with this underbar. So what I show is it's a vector, it's not a continuous value. Sometimes you might have learned overbar, it doesn't matter. So I'm going to use underbar because that's what I learned. So suppose those interpolating expressions which I had over here, this x minus x2 divided by x1 minus x2 and x1 minus x divided by x1 minus x2. Suppose I just write them in a vector, and the vector has this shape over here. So it's a vector which contains two expressions, and I'm just going to call this vector n of x. N is, again, this is our vector of shape functions. So suppose I just define these two expressions as n of x. Again, there's an n bar over here. So it tells you that it's a vector of functions. And this u1, u2, I'm just going to write it in this vector of u bar. U bar is equal to u1, u2. Then what you will see is that u of x, which we had over here, in this expression can be rewritten as u of x is equal to n bar transpose into u bar. Now, why is it transpose? Okay, I'm assuming that this vector n bar, for example, is of size 2 by 1, and this u is also of size 2 by 1. I cannot multiply, if I try to do n into u, I cannot multiply a 2 by 1 vector with a 2 by 1 vector. The last size of the first vector is not equal to the first size of the second vector, and so I can't actually use this. Whereas I know I need a final expression. This expression is not a vector, it's a scalar. So this is actually 1 by 1, which is a scalar. So I need to multiply these two vectors in such a way that I end up with a scalar. It so turns out that if I do n transpose is going to be 1 by 2. And I hope you've studied linear algebra, you know what transpose means. So if n is 2 by 1, n transpose is 1 by 2 into u, and u is again 2 by 1. So this multiplication is going to give me 1 by 1. So that's basically why, because we know we need a scalar as the output, we put this n transpose over here. We could also do u transpose n, and in some applications we do. There is a good reason why we do n transpose u. We'll get into that later. Okay, so using this particular notation, and now what I do is I simply plug in x1 is equal to minus 1 and x2 is equal to 2. Plugging in this notation, I just get the formal form for this particular problem. I get a formal form of u of x, which is this 2 minus x over 3 and 1 plus x over 3. Those are what we call our shape functions, transpose into u1 into u2. Now, what we know is that, so basically what we have is we have a system of equations. We have the following system of equations. We know that whatever solution we get, it must satisfy the two boundary conditions, that u1 is equal to 0 and u2 is equal to 0. So whatever we have over here, we can substitute u1 and u2 is equal to 0 into this right hand side. Interestingly, when we substitute u1 is equal to 0 and u2 is equal to 0 on the right hand side, we actually just end up getting u of x is equal to 0. So for a assumption that we are going to discretize our domain into two nodes, and those nodes are connected by some kind of a linear function, a linear shape function, which is a completely arbitrary assumption. But for this assumption, we get a solution u of x is equal to 0. If I plot it, this orange line represents the solution which you just got. So this is the FEM solution, this orange line. And this again was the analytical solution. I think you will agree with me that it's not a very good solution, right? We have this sinusoid, this quadratic sort of shape for the analytical solution. And our numerical solution is this flat line, u is equal to 0. So clearly we managed to get a solution. It wasn't a particularly good solution. Okay. So why did this happen? Why is it that we got such a terrible solution? Let's go back and look at our ordinary differential equation again. Now, what we define is, in the finite element method, we define something called a residue. The residual is basically left-hand side minus right-hand side of the ordinary differential equation. So if this is my ODE, then my residual is going to be defined as, these three lines basically is a notation that says defined as or is equivalent to. These are defined as d square u minus dx square plus u minus 2x square. If u were the analytical solution, that if u exactly satisfied this differential equation at every point, then we know that this residual is going to be 0 because it's the exact solution. So if the left hand side were exactly equal to right hand side, then the residual would be 0. But recall that the finite element solution does not give us an exact solution. We are carrying some error in our solution of u, and therefore my left hand side will not be exactly equal to the right hand side. In other words, this residual r of x will not be equal to 0 in the finite element method. So that kind of is built into the finite element method. We know that we are not going to get a residual equal to 0. So if you look at the previous problem, we had an approximate solution which was u of x is equal to 0. If you plug that into this form over here, then you basically are getting d square of dx square of 0 plus 0 minus 2x square. So we get the residual of minus 2x square, which clearly is not 0 for all x inside the domain. So you can clearly see that for this solution, we should not have even expected to get a good solution because we are carrying a fairly large error, which is this minus 2x square. So then what do we do to get a better solution? Obviously, we'd like a better solution. How can we get a better solution? Now, again, this is meant to be an overview of FEM, so I'm not going to go into every detail. I strongly recommend all of you to take a proper class on FEM so you learn more of these details. But here is the general way of looking at the solution. We cannot guarantee that r of x is going to be equal to 0 at every point. It's just not possible to do it in the finite element method. Instead, what we say in the finite element method is, can we at least have some kind of total solution or a weighted total solution to be 0? For example, if we go back to this solution, so if we have this, we cannot guarantee the solution is going to be 0 at every point. Can we at least guarantee that the solution maybe looks like this, that the solution undershoots at some points and overshoots at some points, but on average, the total solution is still 0? In other words, in the finite element method, while we cannot guarantee that r of x is equal to 0, we cannot do this. We try to at least say that the total residual, that the integral r of x dx, that's just a way of writing total residual, that this is 0. This is something we can try, but as it turns out in the finite element method, this particular solution which I've drawn over here, so this area is approximately equal to this area, approximately equal to this, so on. So the total, because some of the error is positive, some of the error is negative, it turns out that this extremely bad solution which I just drew on top of my analytical solution, this will actually come very close to satisfying this condition, that this integral of r of x dx is equal to 0. Somewhere you have a very large positive error, somewhere you have a very large negative error, and so the two cancel out when you add them. So if you just do this integral of r of x dx, you will get a solution, you'll get a pretty bad solution. So what we actually do in the finite element method is, we don't assume that this total residual is 0. We assume that some weighted residual is 0, that we multiply by the residual by some weight. And we hope that the total weighted residual is 0. And that is also why we call this particular approach to solving the problem as WRT, the weighted residual technique. So WR stands for weighted residual. So within each element, we instead of hoping that we get total solution of 0, we assume that our total weighted residual is 0. And the choice of this weight, which sometimes we call the test solution, it's up to us what we want to do. We generally assume that it has a similar functional form as the original solution. So our original solution, we had said u is equal to n transpose of u under bar. So we say that our weight, which is completely arbitrary, we can choose any weight we want. We assume that the weight is also some w bar transpose of n. So we assume that both can be approximated using the same set of shape functions. That is an additional assumption which we make in the weighted residual technique for the finite element method. Okay, so continuing on, so we assume that the total weighted residual is this integral wr dx is equal to 0, where we choose u of x is equal to n transpose of u, where n transpose is an arbitrary shape function that we decide, and u is the solution at the nodes. And similarly, we choose that w is w transpose into n, where n is the same set of shape functions. So it's the same arbitrary shape of the solution as u into some w transpose, so into some other constant vector. So then what if we do that and we plug in for this particular expression, we get the weighted residual as this integral from -1 to 2 w of x into this residual over here. Again, recall we made this assumption for u. One problem over here, what we see is we have a d square u over dx square. D square u over dx square means we have to have a second order derivative. So we have to choose an expression for u which actually has a second order derivative defined. One way to write that is we have to assume that u is C2 continuous. That is, you can define a second order derivative. For various reasons, which I'm not going to go into in this class, that is an inconvenient requirement. It can lead to variety of errors and a lot of difficulty in solving the solution. So what we instead do, we usually perform a technique called integration by parts. I'm sure all of you learned it in high school. You may want to go back and do a quick revision on it. We perform integration by parts where we actually reduce this particular expression. So instead of having w into d square u over dx squared, we perform integration by parts on this and we split the derivative half on one side to w and half to u. And so substituting then our finite element approximation, this is what our solution becomes. Note that we'll basically have a w transpose on both sides. So both of them can be cancelled out. So this is what we get as our expression. We get some sort of expression which is dn into dn transpose in minus nn transpose into u. U is a constant, so we can take it out of the integration, is equal to some sort of a vector on the right hand side because n is a vector. It's into some 2x square and some integration has to be performed. Let's take a look at this for a second. So this, or we can look at this term. So this is nn transpose. N is of size 2 by 1 and n transpose is going to be of size 1 by 2. So this nn transpose is actually a 2 by 2 matrix. So what we are actually getting is we are getting a 2 by 2 matrix into a 2 by 1 vector is equal to 2 by 1 vector, which mathematically is correct. We generally write this in compact form as ku is equal to f, where k was this term which we derived in the previous slide. K is called the stiffness matrix. All the physics of the problem, everything on the left hand side basically of the problem is encoded in the stiffness matrix. F is what we call the source term. In some applications, particularly structural engineering, it's also called the force term. So either source or force. This encodes the external stimulus applied on the system. So it's the external force or the right hand side of the system. So what we've done is we've taken this original differential equation, and now converted it into a series of linear equations, algebraic equations of the form ku is equal to f, where this k is the stiffness matrix and f is the force vector. This is the basic idea of the finite element method, that we get k, we convert our system into k is equal to f, and now we solve a series of differential equations. Now, there is one more thing called local support. We'll actually talk about this in the next class. So as we said previously, in the finite element method, we assume that each element satisfies ku is equal to f. Previously, we had our domain and we cut it only into two nodes, so one element. But we could have more nodes, and each node can be connected by each element. We assume that this stiffness matrix is only valid inside this element, and the next element has its own stiffness matrix. The next element has its own stiffness matrix. So a stiffness matrix is only defined within a particular element. That's an assumption we call local support. Based on this, we can create what's called a global stiffness matrix. We'll see more details about this in later lectures. Now, when you do that, then, when we did that, I went ahead and did the solution. And basically what I did is the same solution, I increased the number of elements. So previously we had one element and we saw our solution was basically this flat line, 0. It was a pretty bad solution. What I did is I just increased the number of elements and solved this differential equation using the finite element method. It's a little difficult to see, but the very last line, very difficult to see, but the very last line is actually the exact solution. So what you see is as I increase the number of elements, I'm getting very close. I'm never exact, but I'm getting very close to the analytical solution. Another way to write it is, as my number of elements tends to infinity, it will never actually be infinity, but as the number of elements tends to infinity, the error tends to 0. That is the main advantage of the finite element method. Disadvantage, of course, you have to do so much mathematics, you have to write a computer programs, etc. All that's there. The advantage is that as long as we're willing to tolerate a small error, we know we can get a good approximate solution for a finite number of elements. So we don't actually want error to be zero. As long as we're willing to tolerate a small error, we can get a pretty good solution, as you see in this graph, using the finite element methods. And so this figure, I'm showing the same thing, that this is the analytical solution. And as the number of elements increases, the solution is getting very, very close. It's never exact, but it's getting close enough that for engineering applications, we can work with it. So anyway, so that was a lot on the finite element method. Again, you have to take a full-fledged class to go into a lot of details. But in the next lecture, what we're going to do, we're going to see how finite element methods can actually be applied for rigid pavements, which is the purpose of this series of lectures. So I'll see you in the next lecture. Thank you.